Okay, so today in office hours we are looking at prep activity 2, predicting reactions, categorizing reactions, and we're particularly going to look at reaction 3 and reaction 8. And one of the things that's interesting, I was talking about this before I started recording, when all of you look at these two reactions, you probably see these two reactions and are like, oh, they're not related. But when I look at them, I'm like, oh, I see how they're the same. And that has to do with this kind of general, how do we categorize chemical reactions? How do we make sense of what's actually happening? So reaction 3 first, and then we'll get to reaction 8. Reaction 3 is magnesium metal reacting with hydrochloric acid, aqueous. And it even gives us a hint. It says we're going to have product 1 and product 2. So when we start trying to predict products, one thing we'll notice, the place I like to start is I like to say, okay, what's the charge on each thing as it is in its reactant state? Magnesium by itself is going to have 0 charge, right? Remembering that this is lowest ratio, so if there's a bunch of magnesiums next to each other, they can't be positively charged, or they would all push away from each other. So it must be, and magnesium has very low electronegativity, so it's not going to be negatively, it's never negative. So it must be neutral. HCl, we've got hydrochloric acid. We've got a covalent bond here. Our hydrogen is typically a +1, our chlorine is typically a -1. And as soon as I see a reaction with something that's got a 0, I'm already thinking about one of my possible types of reactions for my chemical type. It's easy to jump to the fact that there's acid here to think acid-base. And we've also got something aqueous and something solid, so precipitation is not very likely, but the charges kind of give us another hint. Now, I'm going to do single displacement in this case, right? I can't do double displacement. I've got 2 things here, but I've only got 1 thing here. So if I'm going to do a displacement, it's going to be a single displacement of magnesium replacing hydrogen. Recognizing from our periodic trends that magnesium can become positive, it can be the thing that ends up being a cation. So I'm going to do single displacement, magnesium chloride, and hydrogen. Now, we have to fix our products a little bit. So we're going to go back to this idea of charge. Chlorine is still a -1. What's the typical charge going from the periodic trends, kind of the things we learned in week 4, was that? Week 3? I can't remember. Week 4. Also, always handy, periodic table handy. What's the typical charge on magnesium?
Is it +2?
It is +2. So when I look at the fact that magnesium's +2, chlorine is -1, if I want to charge balance this, I need 2 chlorines. So I've got +2, -1, -1, I've got a neutral compound. So that's charge balance, that's looking good. Hydrogen, on the other hand, right now this could be a hydrogen. This is just representing hydrogens kind of floating around. But if we have 2 hydrogens next to each other, what happens? They bond. There's a couple different ways to think about what's happening with hydrogen and why we get H2 to make our good compound. One is we can just remember our diatomic gases, HONClBrIF. Those things just form 2s. The other way we can think about it is if you had a hydrogen next to another hydrogen, in order to complete that valence shell, you form a covalent bond between 2 hydrogens, and this would represent a covalent bond between 2 hydrogens, right? That's going to give both hydrogens a full valence shell, and that's going to create some stability. To get states of matter on these things, for magnesium chloride, I'm going to go to my solubility rules. Also, let me know if I'm doing too much detailing. You're like, no, I get this part. I can go quicker. But I go to my solubility rules. Rule number 3 on the soluble side says chlorine is soluble with a few exceptions, but magnesium is not one of the exceptions. So this is going to be aqueous. And then hydrogen is one of our diatomic gases, so that's going to be a gas. That is predicting our products. Now, at this point, we've got our predicted products. We've got good compounds for our predicted products. So now we can go back and balance this reaction. If you try to balance the reaction before you've got good reactants, good products, you get nonsense, right? And that's one of the things we really have to be careful about when we start doing chemistry on paper versus chemistry in the physical world. On paper, we can write down all kinds of nonsense. But what we want to write down is what actually represents what happens in the physical world, right? Everything we're doing in this class is trying to represent stuff that we see happen in the world around us. Can we write nonsense? Yeah, I could make this magnesium 10 trillion reacts with 50 billion hydrochloric acids, and just like I could make anything. I could say that this is H27Cl. It makes no sense. We wouldn't do that, right? We want to represent what's really happening. And what's really happening is just a rearrangement. So if I have 2 chlorines on this side, I need 2 chlorines on this side. Now, I can't change my compound after I have a good compound. I can't make this Cl2 because it's already charge balanced. But I can say that I've got 2 HCl's and there's going to be 2 hydrogens, 2 chlorines for that. So then that's going to be 2 chlorines, 2 chlorines, 2 hydrogens. Oh, look at that. How convenient. 2 hydrogens, 1 magnesium, 1 magnesium. All I've done is rearranged my elements. I haven't created anything new. Now, type of reaction. There are signs for what's happening for the type of reaction. Precipitation reactions, we usually have a solid formed. And we have no solids formed, so not a precipitation reaction. Acid-base reaction, we usually see acid as a reactant. Oh, we've got that. And we see water as a product. We don't have that. So this does not look like an acid-base reaction. And I usually, side note, in my logical progression, I usually do those 2 first because they're a little bit easier to do. Redox reactions, because they can do so many different things, it's harder to see them until you get used to it. But after you get used to it, I think redox are actually really easy once you get used to the charges. Redox reaction, we're looking for a change in the charge on the element. Magnesium goes from 0, let's go with this one. Magnesium goes from 0 to +2. That means it has lost negative charges. It has lost its electrons. And what's picked up those electrons is this hydrogen. Hydrogen ends up with a 0 charge. So we've got something that loses electrons, something that gains electrons. This is actually really important and really kind of nice symmetry that exists in the world, right? We never create electrons. We always get electrons from one thing over to another thing. So the electrons are essentially being ripped off of the magnesium by the hydrogen. We could, if we wanted to go further in our chemical understanding, we could make sense of this from the electronegativity difference. Excuse me. We could make sense of this through the electronegativity difference between hydrogen and magnesium and chlorine with a minus charge. And we could say, well, is magnesium going to rip electrons off of chlorine? And you're going to say, no, chlorine's too electronegative. It's going to pull electrons towards it. It's already got negative charges. Hydrogen versus magnesium, it turns out hydrogen's more electronegative, and it can rip electrons off of magnesium. Let me ask you, is what Emmy, you asked this question, right? Yeah. Are you taking Chem 125, 128 in the future?
No.
Okay. Well, then you're going to miss out on what I think is a really fun topic in chemistry, electrochemistry, where we actually look at the energy associated with these reactions and come up with an energetic reason for why this happens. We're not doing that this quarter. This quarter, we're just recognizing the patterns of what we see happen, not why it happens. So if I were to categorize this reaction, it's redox because I've got my reduction and oxidation happening. Big signs for redox reactions: if you ever end up with things in zero charge states, neutral elements, that usually means there's a redox reaction going on someplace. Other good, really obvious sign, not in this reaction, but I think in reaction 8, if the number of oxygens attached to something changes, that's another really good sign that oxidation reactions are occurring. So those are the big tells. But the actual tell is change in charge, right? Hydrogen going from +1 to 0, magnesium going from 0 to +2. This would also be single displacement, right? It's not double displacement because I'm not flipping two things, I'm just flipping one thing in and one thing out. So it's also a single displacement. Good? Questions on that? Is that good? Okay.
What about the metathesis?
So metathesis, I think is a Latin word. Metathesis is the fancy way of saying double displacement. You could also call it what I usually call it, which I just call it flip-flop reactions. Right, because you flip and you flop. Double displacement, or if you want to sound very scholarly, oh yes, the metathesis reaction.
Are all metathesis reactions precipitation reactions, or no?
No. Right, and that's where it's two different categories. A lot of precipitation reactions are metathesis reactions. Not all, but a lot. And there are a lot of metathesis reactions that are not precipitate. A lot of acid-base reactions are also metathesis.
So on mine it said, I put it was metathesis, and it said it was right.
For calcium metal with water?
No, for magnesium with hydrochloric acid.
Oh. Let me check something.
And it says it's wrong without it.
So when I go ahead and look up the definition of metathesis in the textbook, this is kind of the first sentence. A precipitation reaction is one in which dissolved substances react to form one or more solid product. Many reactions of this type involve exchanging ions between ionic compounds in aqueous solution and are sometimes referred to as double displacement, double replacement, or metathesis reactions. These reactions are common in nature and responsible for the formation of coral reefs, ocean water, and kidney stones in animals. So from the definition of metathesis that I'm comfortable with, I would say it's a double displacement reaction, not a single displacement. So I disagree a little bit. Which problem was that? Was that problem 3?
Yeah.
So I'll double check with the instructors about whether that's actually a metathesis reaction or if it actually is technically a single displacement. And maybe there's... I also don't study organic chemistry. And that's where most of this stuff is used. I do the P-Chem stuff, the stuff from like week 2, week 3. So there's also a possibility that there's a broader definition that I'm just unaware of. And so I'll double check with the other instructors and make sure we get that cleared up. And
one quick question on that, Tom, if you're
sure,
ready.
absolutely, yeah.
Can you just briefly go over like why Mg is a +2 charge?
Okay, so why is Mg a +2 charge? This goes back to material from week 4. We're going to pretend, well, I'll just hold up a periodic table. So if we're looking at periodic table, can you see that okay? I have trouble. I'm small on my screen, so I can't tell how big this is. If we're looking at a periodic table, we know we've got high electronegativity, low electronegativity, and the goal in pretty much all electron motion is to try and get to this noble gas-like configuration, that stable type configuration. Whether it's easier to gain electrons to do that or lose electrons to do that, that's what we're going to try to do. Of course, it depends on the environments we're in. If it's sitting outside in the air, that's one situation. If it's deep underwater in high pressure, low oxygen environments, that's a different situation. But generally, if we're just talking about things that humans interact with, surface of the Earth, we're going to get that noble gas-like configuration. And when we look at magnesium, it is a 3s2 electron configuration. So we could try to force 6 more electrons around it, or we could take 2 electrons away from it. Now, given that it's all the way on the right-hand side of the periodic table, it's very low electronegativity, which means it doesn't pull electrons towards it very well.
Mm-hmm.
So it's going to lose electrons, and if it loses 2 electrons, we get that noble gas configuration.
Mm-hmm.
And it turns out that's true for everything below magnesium as well. So everything in that second column typically forms a +2 charge.
Okay. That makes sense.
Yeah.
And because just Mg by itself has no charges because it's not like bonding with anything else.
Yeah, so, and this is where the language of the problem becomes really important, right? We could have said magnesium ions thrown into acid, but that would have been boring. But this is just magnesium. And when we say just magnesium, not magnesium ions, it means like solid magnesium.
Okay. Is it no
So,
charge?
one magnesium next to another magnesium next to another magnesium. If the magnesiums had charge, they would all end up pushing away from each other and you wouldn't form a solid.
Okay.
So it has to be
Yeah.
neutral.
That makes sense.
With that in mind, let's go ahead and look at, that's reaction 3. Let's go ahead and look at reaction 8. Okay, so reaction 8 is actually going to be not dissimilar from what we just did. A few grains of calcium metal combined with some water. So we're going to be looking at calcium solid plus H2O liquid. Now already, as soon as we see calcium by itself in its neutral state, we should already be like, oh, that's already starting to look like it might be redox. Already. So calcium metal with water. I'm going to write water in a little bit of a different way because I feel like it makes it easier to see the displacement reaction. Sometimes it's better to think about water as a hydrogen attached to a hydroxide. Really, it's the same thing. Whether we've got it written as H2O, this just kind of suggests the idea that like a hydrogen could leave, a hydroxide could be left behind. So when we look at it like that, we can kind of see this same single displacement idea. The hydrogen is going to have a slight positive. The hydroxide is going to be negative. And we're going to see the same kind of single displacement idea we saw here, where when calcium, again, if we look at the periodic table, calcium is right below magnesium on the periodic table, so it's not surprising that it has similar reactive behavior. Calcium is going to form a +2 charge replacing that hydrogen. So I'm going to end up forming calcium hydroxide and hydrogen. Again, before we balance, before we start trying to say anything about this reaction, we have to make sure that we've got good reactants and good products. Reactants are fine. We've got calcium, we've got H2O. My products, typical charge on calcium, looking at our periodic tables, it's right below magnesium. It turns out it forms a +2. This hydroxide, we must need 2 of those -1 charges in order to balance it. Right, so we've got +2, -1, -1. That gives us a neutral compound. And hydrogen doesn't like to exist by itself. If there were 2 hydrogen floating next to each other, they're going to form molecular hydrogen. This, if you ever have a hydrogen just by itself, it's so uncommon it gets a special name. We call this atomic hydrogen. Whenever we just say hydrogen, we almost always mean H2. This is gas. Calcium hydroxide, if I remember correctly, this one's a little bit weird. Is calcium hydroxide solid or aqueous? So we'll talk about that in just a moment. I'll just put it with a question mark for now. I'm going to balance this chemical reaction before we go too much further. I've got 2 hydroxides, so I'm going to put a 2 here. That's going to give me my 2 OHs. That's also going to give me my 2 hydrogens. That's balanced. I can see the same kind of redox reaction happening. Loss of electrons from the calcium, gain of electrons to the hydrogen. Really, actually, very similar to reaction 3. Okay, back to the calcium hydroxide issue. Because I think LabPal's looking for you to say it's solid. And here's the problem. We got our solubility rules. Insoluble rule number 1 says hydroxides are insoluble except with group 1 and large group 2, starting with calcium. Now that would mean large group 2 starts with calcium. Calcium should be soluble. It should be aqueous in solution. The reason that this isn't exactly true is because this is, I used this phrase, I answered this in on the discussion forums this morning, and for some reason I was feeling like using really big words, so I referred to this as a false dichotomy of solubility. That is to say, it's an oversimplification. It's too simple, right? This idea that it's soluble or not is too simple. Think about this. Does sodium chloride dissolve in water? You can just nod yes or shake no for those that I can see. Yeah, of course it does. Does it dissolve in water forever? No, of course not, right? So if I had a cup of water, there's a limit to how much salt I can pour in for it to dissolve. Now, this idea of soluble and insoluble has a particular arbitrary cutoff. That is to say, scientists kind of decided if more than 1 gram dissolves, we'll call it soluble. If less than 1 gram dissolves, we'll call it insoluble. Kind of an arbitrary cutoff for whether it's soluble or not. And it turns out calcium hydroxide straddles that definition. So about half the people you ask will say calcium hydroxide is insoluble, and half the people you ask will say calcium hydroxide is soluble. Because its solubility is right at that boundary between what people consider soluble and insoluble. So it's harder, it's not just as simple as it's one or the other. There's more to it. Based on our solubility rules, though, this should be aqueous. However, I think the LabPal has it as solid. And I'll make a note for that as well.
Yeah, that was the problem. Thank you.
Right, and this is because sometimes when instructors are doing this, and I will admit, if I find some of the old versions of the equations sheet, equation sheets that we used like 2 years ago had different solubility rules on them. Just little tweaks, little differences, but enough that if I used an old equation sheet to make an assignment, everyone got the question wrong because they had slightly different solubility rules. So I'll check in with the other instructors about that one as well. Let's see what we got on here. Emmy and Jessica, was that for reaction 8 or reaction 3 that it was still giving you a wrong answer? For both. Okay, I'm going to pause recording since this seems like more... Okay. So, to continue, next questions are mastery questions set 9, problem 3, and problem 4. And these are pretty fun. Now these, okay, who asked about these? Because I got to tell you, I'm pretty sure it's got some randomized values, so you might have a different reaction than what I've got displayed.
I did.
That was you, Dylan?
Yeah.
Sorry, I was just scrolling back to see where it was. Actually, we'll talk about that in just a moment. I think how many points is problem 6 worth? Because there's an error that happens if that's the case. So, but let's focus on, yeah, so it always turns green if it's 0 points. But we're going to focus on mastery question 9, number 3, and number 4 for a moment. Now, tell me if this is the same thing you have. An aqueous solution of lithium bromide, I knew that was wrong, into you mix, reading is hard. Hold on, let's try this again. You mix an aqueous solution of lithium bromide into a solution of copper 1 perchlorate. Predict whether a reaction happens and give the chemical name for the solid that is formed. Good luck.
Yeah, I have sodium sulfide and lithium acetate.
You said sodium sulfide?
Yeah, IDE.
Plus
lithium acetate.
So the first thing we have to do, and if you haven't been practicing your nomenclature, is about to become a headache. Because after doing nomenclature, so we started doing nomenclature in week 4, so we've been doing nomenclature for 3 weeks by the time we get to the quiz this week. When we're kind of at the point where we're like, yeah, you should be able to do the nomenclature. So when we see sodium sulfide, not sulfate, not sulfite, but sulfide, we should know that's Na2S. Charge balancing, sulfide is S2 minus the sodium. We're going to need 2 sodium pluses to balance out the charges. So I've got +1, +1, -2 to give me a neutral compound. It says both of these are aqueous. Makes sense. Lithium compounds typically dissolve in water, and sodium compounds typically dissolve in water. I didn't give myself enough space, so I'm just going to do my products over here. I'm going to do a double displacement, metathesis flip-flop reaction. I'm going to switch my sodium and my lithium and my sodium. And I'm going to do lithium sulfide, charge balanced, and I'm going to do sodium acetate. Sodium compounds, I already know that's aqueous. Acetate, I know is a -1 charge, so this is charge balanced, this is charge balanced, and with 2 lithiums there, that's charge balanced. Balancing the chemical equation, I'll put a 2 in front there. That gives me 2 lithiums, and 2, I'll also need a 2 here. So I've got my 2 acetates, my 2 acetates, my 2 sodiums, my 2 sodiums. Now, is lithium sulfide a solid or not? Looking at my solubility rules, insoluble rule number 3 says sulfide, S2-, is insoluble except with group 1 and group 2. Lithium's in group 1. So this is actually going to be aqueous. So, no reaction. If we go through the process of doing net ionic for your particular reaction, Dylan, everything's aqueous. Everything's got the same charges. Everything's got the same numbers on product side and reactant side. Everything's going to cancel out.
Okay.
Boring. You got a boring combination.
For it to react, the ions have to change? Or?
Something needs to change. Either, there's a couple things we're looking for.
Did the compounds change, or does that not matter?
Not really, and we'll talk about that. State of matter, charge, right, and the reason the compounds didn't actually change is because of what we mean when we say AQ like that, aqueous. Right? This really means that there's lithium floating in solution and there's sulfide floating in solution. They're not actually attached to each other, they're surrounded by waters. This is just the lithium and sulfur in this situation are charge balanced. So what does the sodium sulfide mean here? It means we've got sodium ions floating around in solution, we've got sulfide ions floating around in solution. So if we write this out in terms of the total ionic, trying to represent how the ions actually exist in solution, it's going to take a little bit, but I would have 2 sodiums plus S2- plus 2 lithium plus 2 CH3COO- going to 2 lithium plus S2- plus 2 Na plus 2 CH3COO-, all aqueous. I was a little bit lazy with my state of matter because I knew they were all aqueous already. And this really, this total ionic equation in blue really tries to represent the fact that all of the ionic bonds are interrupted, they're broken essentially by the water dipole interaction.
Interesting.
And so when I actually look at this, I'm like, lithium is in the +1 state in aqueous, lithium's in the +1 state in aqueous, that's the same. It doesn't actually change in this, in our proposed reaction, right? This thing in black is just our prediction of what could happen. And it turns out it doesn't happen. My sodium, same. My sulfide, same. My acetate, same. It turns out that what we wrote down is just nothing. Now, it was a totally fine prediction, but it's not anything. It's not really a reaction.
Cool. Yeah, I didn't see that before.
And then for question 4, this is another one where you can get a lot of different possibilities.
Yeah.
So do you want to try problem 4 on your own for a moment with this extra
sure.
thinking? Okay.
They're similar, so.
Cool. I'm going to... So we have a question here about practice problem that involves this compound. And we're going to be particularly looking at one of the later in this, which is bonding. So we've got this compound. We can go through the first few. How many carbons are in the molecule? How many hydrogens? What's the oxidation state for a couple different things? Average oxidation state, so on and so forth. And then we get to this bonding question, which is consider the carbon-carbon bond between the carbon attached to the nitrogen and the carbon to its left. So we're going to be particularly looking at the carbon that's right here to the carbon that's right here. And we're going to be particularly looking at this bond there. And it says, what's the type of bond? And you're going to write it down in terms of the sigma and whether what it's overlapping. So for example, if you were looking at H2, you'd write sigma SS. So,
Okay. And so what I was thinking was, so since it's a single bond, it's a sigma.
yeah.
And since it's carbon is both in the p orbital, I guess, so it's sigma with two p's.
Yes, but we have to remember when we go from carbon by itself to carbon in a molecule, we have to consider the hybrid orbitals, not just the atomic orbitals. So we have to consider, does that make sense to you so far?
So do C bonded with C, triple bonded with N.
So if I look at the hybrid orbital just on this carbon triple bonded to nitrogen, I can look at this and say it's only got two things attached. So that's going to be
a linear sp orbital.
Linear sp hybrid. This carbon over here should actually have two hydrogens attached to it. This carbon over here should be
sp3 because it's a tetrahedral, or
tetrahedral, four things attached, 109.5, however you want to think about it. There's a lot of different ways to think about this, but it's an sp3 hybrid. And as a reminder, important to me because quantum mechanics, not important to everyone else because, you know, quantum mechanics. The reason we talk about this in terms of an sp is because drawing this line to represent electrons is kind of like a cartoon. It'd be like me trying to draw a tree. Do you know that's a tree? Yeah. Does it actually look like a tree? No. Right? And it's this idea of how we represent things. Do we know this is an electron cloud? Yeah. Does it look like an electron cloud? No. So how do we bring back in that idea of the electron cloud to our kind of cartoon picture of a molecule? In order to do that, we actually have to go back to the atomic orbitals and how those orbitals interact with each other in a molecule. And that's where we start talking about these hybrids, because the hybrids are going to give us a better, it's essentially like making this picture of a tree better, right? You know, if you get someone who's better at drawing, you can get a better picture. So the hybrids give us a better idea of what the electron cloud looks like around this carbon and what the electron cloud looks like around this carbon. And by putting those together, we can get what the electron cloud looks like between the carbons. So this would be a sigma sp3 dash sp.
okay, so what it's asking is like, okay, so between the two carbons.
Right. So you're right that it's a sigma. And really that has to do with the symmetry of the bond, not just whether it's single, double, triple, but single fine. So we've got the fact that it's a single bond, so it's a sigma. But it's a single bond created by this electron cloud interacting with this electron cloud.
Okay, so that's what it's. So it's like you look at the individual atoms and say, okay, what's the geometry? And then that's, okay, I see.
Yeah. So we look at the individuals. Now, if we want it to be even more correct, we would go all the way to molecular orbital theory. But we barely touch on that in Gen Chem in our third quarter, because it takes a lot to get to it. But there's an even better answer than this out there. Cool.
Stay tuned.
Just a quick question